Good day, I'm Dr. T and welcome to my office. So today I'd like to talk a bit about smelting. Smelting is the process of taking a metal's ore, which is basically just a rock. It's a mineral that as a chemist we would look at and call an ionic compound. And these are typically a little bit more complicated than the typical reagents that as chemists we like to use. So this will probably have a couple of different cations, maybe a couple of different anions. But it contains the cation for a metal that we have particular interest in. And we can then smelt that ore. We can take the ore and process it and make the metal. Now, as a species, we've been doing this really since prehistory. The first metals we would have worked with would have been the coinage metals. This is group 11 on the periodic table. For these metals, they can exist in nature as simply a nugget. They don't always exist, and most of the time you don't see them in their nugget form, but this is definitely a common way of seeing it. So you can dig up a copper nugget, a silver nugget, and of course the classic gold nugget, as well as naturally occurring alloys of them, such as gold and silver. That would be a naturally occurring alloy known as electrum. So of course we got used to working with these. And for gold, I mean, really that is the way you find it in nature. The reason you're able to find these materials in nature is that they are very non-reactive. You can do what's known as an activity series. And this ranks metals by how willing they are to react with certain chemicals like oxygen or hydrogen, etc. Specifically, how well they are willing to become oxidized, which means to lose an electron. We call it oxidation because for a metal, the classic one, of course, is things like iron rusting, where it's reacting with the oxygen in the air, giving electrons to the oxygen, and then forming iron oxide. But the chemical term oxidation does apply to any process where electrons are lost. Now, for gold and platinum, the electrons, they're happy with them. They don't really want to give those up. So it takes some pretty extreme chemical conditions for you to get to take those electrons away. For things like silver, oxygen isn't capable of doing that particularly well, but sulfur can do that in certain scenarios. That's why you get this kind of black layer on silver. That tarnish is silver sulfide. And this will be more of a problem if you're in a hydrogen sulfide rich environment. Specifically, the small amount of sulfur that's introduced by burning natural gas. Well, of course, you'll notice that you have to polish your silver a little bit more. But for metals that are a bit more active, they're a bit more willing to give up their electrons, we don't see those naturally occurring in their metallic form in nature. Over time, any that were a metal had simply rusted away into their oxide or their sulfide or some other inorganic compound containing them. So as humans, of course, we've got our small amounts of gold, silver, and copper nuggets. And of course, fire is a thing, and we build fire with rocks, and certain rocks contain minerals that contain the cations for lead, which is very common, as well as those for tin. Now, both of these, you can react with the fire and actually convert that into their metallic form. And this would be like a campfire. So in order to do this, this is called reduction. The name comes from smelting, where if you take, say, a ton of ore and you smelt it, you're only going to get, a part of a ton of your metal, depending on obviously what your metal is, what your ore is, lots of conditions. But, you may only get half a ton out of your ton, so you're reducing down that ore into the metal and then, trash that you throw away, the slag. So to do that, to do this reduction, what you need to do is be able to give the metal electrons. This is the opposite of oxidation. In fact, there's always both of them taking place. So when the sulfur reacts with silver and it oxidizes the sulfur is reduced. It's accepting electrons. So for reduction, to smelt your metal, you need a source of electrons. And for a lot of cases, this is going to be carbon monoxide. So if you have a fire, typically speaking, what's going to happen is the high heat, if this is, say, wood or a solid fuel, the high heat is going to cause the wood to undergo pyrolysis, where it's starting to degrade from the heat. The complicated cellulose and lignin structures are breaking down and you're forming smaller molecules that then become gases, and those then react with the air. And some of those gases are carbon monoxide. You get a fairly decent amount. That's why if you have, say, a fireplace in your home, you want to make sure the chimney works well and that you have a carbon monoxide detector. Really, if you're doing any kind of open flame or even fairly close flame like natural gas, you still want that carbon monoxide detector just to make sure everything's working good. But that carbon monoxide is capable of reacting with the metal cations. Now for tin and lead, you don't have to get it all that high. Those guys will melt fairly easily. You're able to separate them apart and you get enough energy just from your campfire in order to start smelting them. You have to have enough energy to get that reaction to go. Now with copper, this would have probably been the third one starting to be smelted. And in this case, a campfire is a little bit too low of a temperature. You're going to have to go a little bit hotter. So the thoughts are maybe that this was discovered at the same time pottery kilns were a thing, because you want to get the temperature a bit hotter. Now, interesting enough with copper, if your ore is a copper sulfide, the sulfide is actually going to be able to be your reducing agent at very high temperatures with a modest amount of oxygen in there. The sulfur will oxidize. It will form sulfur dioxide, which will then eventually turn into sulfuric acid if it gets wet. It reacts with water, or it will turn into a couple other compounds, just kind of down the road. But in that process of oxidizing, it will give up its electrons potentially to the copper, and thus you can smelt copper. You don't actually need the carbon monoxide for the copper, although hey, it's going to help. At least I think so. I don't smelt for a living, but general idea here. Okay, now with iron, this would have been a little bit later on, and the trick with iron is you need very high temperatures. So the earliest iron smelting is going to be done with bloomery furnaces. And so in this case, we're getting it really hot, but we're not getting it so hot as the iron fully melts. So instead, you get the slag melting away. So this is going to be things like silicates, etc. And effectively, you get molten glass, and this is going to have these kind of poofy metal globs called blooms that then you pound into wrought iron. Now, if you see the pictures of the blacksmiths and they're pounding on it and sparks are flying, the sparks are from slag that wasn't purified during the smelting process because it wasn't melted. Crucible steel, which is what we use nowadays, takes it up even higher in temperature and actually fully liquefies the iron. And in that case, then the slag separates out and will float in the top. You skim off the slag and you pour out the iron, and now you got a much higher quality iron. This had been known really since antiquity in certain parts of the world, but it wasn't very widespread up until really fairly recently. Once the Industrial Revolution is starting to kick off, and we get like the Bessemer process. So with that said, that's a brief introduction to smelting. Now the next thing that really goes with smelting is starting to realize this goal of alloys. And alloys are going to be starting to mix different metals together. Or even different things that are not metals, so like carbon and steel. And thus taking, instead of having a pure metal, which is actually very, very hard to do. Unintentionally, primitive metallurgists would be getting alloys just because that's the other stuff that was in the rocks they were dealing with, and they were getting trace amounts of this. And so if you would source things differently, with one of the first major alloys that really kind of revolutionized things was bronze. And that is an alloy of mostly copper, but some tin. Now, the interesting part is bronze is that tin is actually the rare part. So that was the one that would be a little bit more difficult to acquire. Copper is reasonably common. Tin is much harder to get a hold of. And with this, you can make a very nice hard metal that holds an edge fairly good, makes a nice tool. Copper by itself is too soft. The atoms within the copper flow past each other just too easily. You need atoms of a slightly different size in order to wedge in there and make them a bit more rigid, and that's what you get with bronze. So with that said, that's a little brief introduction to smelting and metallurgy. As chemists, we have really kind of taken some of the ideas and run with it, specifically the redox, the reduction and oxidation, which is definitely a very useful thing for us as chemists to think about, because a lot of chemical reactions will do this, even though it's not quite so obvious as it is with the metals. So with that said, have a wonderful day.